Every year, the world produces more than 1 trillion bricks. They are a silent part of our homes and of what we understand as progress. They are there and we don't notice them because in the midst of comfort no one asks. How much that is one cost the planet? They come from fertile soils that do not regenerate, and each ton emits more than 200 kilograms of carbon dioxide, consuming 706 kilowatt-hours, enough energy to power an average home for 10 weeks. In addition, just the walls of a single house require more than 4,000 bricks, which mean emitting between 2 and 4 tons of CO2 into the atmosphere. On a global scale, this is still being construction. As Antoine Lavoisier once said, nothing is created, nothing is lost, everything is transformed. However, in this sector, we are still losing too much. If we have advanced so much, why are we still manufacturing them the same way as more than 1,000 years ago? Even knowing that their waste does not disappear, it can be broken, crushed, turned into powder, but it will remain. But what if that waste were not the end, but the beginning of a new material? From these residues, it is indeed possible to form a new material. Recycled brick powder, rich in silica and alumina, can like alkaline activation and reorganize into a stable network with cementitious properties. This is known as geopolymer materials.
Unlike conventional brick, this process doesn't require curing at high temperatures. Studies have shown that geopolymers can develop at a room temperature or under moderate curing condition, with values close to 60 degrees Celsius. In addition, they reach compressive strength of up to 32 megapascals, with lower absorption rates and reduction in drying shrinkage of up to 35%, which improves the dimensional stability of the materials, complying with TMS 402 regulation and other international standards in America and Europe. However, not everything is so simple, as thermal comfort decreases as the matrix densifies and reduces the permeability of its pores. Additionally, the grading process and the mixture with conventional activators necessary to achieve geopolymerization increase cost. Here is where waste change the focus again. Science is not in a single place. It comes from different sources with diverse composition and characteristics. However, it's precisely that diversity that opens up new possibilities. Today, waste such as plastic, oils, and other byproducts are already being reused in agriculture or energy production, reducing cost and pollution. For us, this poses direct challenge in the way we build. The goal is to design a brick capable of meeting standards such as ASTM C90 and ASTM 62, using waste in a way that even emits 80% less carbon dioxide than common method. An idea that is beginning to take shape as a real impact on the decarbonization of the construction sector. But is it possible to manufacture bricks with what is commonly known as a garbage?
The response appears again in the same place, and a second curiosity materializes this possibility. Rice husk ash, an agro-industrial residue derived from a global rye production that exceeds 776 million tons annually. This high production volume generates large amounts of waste, whose valorization represents a sustainable opportunity in the construction industry. By incorporating 5% of this ash into the brick powder mixture, the high content of amorphous silica manages to modify the thermal response of the material, making it comfortable and functional. At the same time, it also achieves an increase in initial strength surpassing 40 MPa. But it's not all about the fines, as the activators, which allow the reaction to occur and transform the combination of rice husk ash and brick powder particles into a structural material, are essential for the system to truly function as a whole. Without them, there is no matrix, there is no cohesion, and therefore there is no brick. Conventional activators, such as sodium hydroxide or silicates, concentrate a large part of the cost and environmental impact. As long as there's no continuous sustainability will end up breaking down. For this reason, it is proposed to use alkaline solution recovered from industrial effluents from sectors such as textiles, chemicals, or treatment plants as a viable alternative. These wastes usually contain alkaline compounds capable of activating the dissolution of aluminum silicates, allowing the induction of upolymeration in a manner similar to commercial activators. The reuse not only reduces the need for high-cost chemical inputs, but also decreases the environmental impact associated with their production and final disposal. Integrating into the circular economy approach we propose, thus, when a system stops relying on what generates the problem, it begins to sustain itself on its own coherence. Under this hope, brick ceased to be a conventional material to become a sustainable alternative capable of meeting the demand of world constant growth, urbanization, and industrialization.
A material where waste stops being a problem and becomes the starting point to design, innovate, and build in a more efficient and sustainable way. As an old proverb warns, only when the last tree has been cut down, the last river poisoned, and the last fish caught, we will realize that we cannot eat money. We are still in time to avoid it, and also to build better, with less and for more. We are not just proposing a new brick, we are proposing a new way of building, one that takes what we discard today and turns it into opportunity, where each brick stops being just a construction element and tells a story of innovation and sustainability. The technology is ready. The question is, are we?